Hello, ladies and gentlemen. Um, we begin chapter 4 today, and we'll start with section 4.1 and move on to 4.2. So let's get started with a white. Okay, so 4.1. So this is about random variables, so-called random variable. The whole chapter is about random variables. So let's start with S, a sample space. That's just a set. And I want the set to be either finite or countable. Countable means that you can put the elements in one-to-one correspondence with the natural numbers, the counting numbers, okay? And so let P be a probability rule on S, meaning for every subset of S, we have a way of associating a number P of E, it's a real number, and this is just review. You know that the real number must be between 0 and 1. You know that P of the entire sample space is 1. And you know that if E and E1, let me just use the general form of it. If you have a sequence of events, keep going, and EI intersect EJ, they're mutually, every pair of events in the sequence are mutually exclusive, so pairwise mutually exclusive, then the probability of the union of all the EIs, I goes from 1 to infinity, is the sum, I equals 1 to infinity, P of EI. Okay, so I'm now ready to define what I mean by a random variable. So here's the definition. A random variable is a function x going from S to the real numbers. It's a strange name because it's a function and not a variable, but the idea is that if S consisted of a single point, then a random variable would be a function from a single point to the real numbers, a single element to the real numbers, which would just be a real number, and that would be a variable real number. And that's where I think the terminology comes from, although I'm not sure. Okay, so that's all it is. It's just a function from the sample space to the real numbers. In physics, it's also called an observable or a measurement. What I mean by physics here is quantum physics. I'm going to give you some examples. Okay, so example 1, let's flip a fair coin 3 times, and let's record the sequences. And so what is the sample space? Oh, and I want X to be the number of times head appears. Heads appears. So the sample space here has 8 elements. It would be like H, 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 T, H, T, H. So this is an order triple where the first term is the first flip, the result of the first flip. Second term is the result of the second flip, and the third is the result of the third flip. So there are 8 possibilities. And so, for example, if we want to compute the random variable evaluated on the tuple H, H, T, There are two heads in that tuple, so that would be 2. So that's an example of a random variable. So here's another example of a random variable. Let's roll a pair of fair dice, not crooked dice. And then there are 36 outcomes according to what the dice show when you roll. And so it'll be A comma B, where 1 less or equal to A is less or equal to 6, and 1 less or equal to B is less or equal to 6. Okay, so 6 times 6 is 36. There are 36 outcomes. And then we have a random variable x going from the sample space to R. X evaluated at an outcome AB is A plus B. All that is you're recording the sum of the dice. Okay, so that's a second example. So now I'm going to move on to some definitions, some very important definitions. First, some notation. If X is a random variable, and A is any real number, we're going to write the probability that X equals A. This is how you read this. This is nothing more than the following. We take the inverse image, the set of elements in the real number, the pre-image of A. These are the set of all elements that map to A under the function. So this is the set of all X in S such that X of X equals A. And this is a subset of S, therefore it's an event, and I could take the probability of that event. And that's the definition of the notation. Okay, so for example, in the example of example 1, which the sample space was flip a coin 3 times, what's the probability that X is 2? Well, you want to, how many ways can you make 2? X is equal to 2 if we get the following situation: heads, heads, tails. We also could get heads, tails, heads, or you can get tails, heads, heads. So that's 3 out of the 8 outcomes give you 2 heads when you toss a coin 3 times. So the probability is 3/8 in that case, 3/8. Okay, so so that's that definition. We have some other other notation. So here's more notation. So we could talk about the probability that X is less than or equal to A. That's by definition the probability you take the set of elements whose value under the function is less than or equal to A. So that would be the probability of the event minus infinity. Take the set of elements that do that, right? So this is the set of X in S such that, ST means such that X of X is less than or equal to A. Likewise, we have X strictly less than A. That would be the probability of the pre-image of the interval minus infinity to A, open interval. And we have the probability similarly that X is bigger than or equal to A. And we have also the probability that X is bigger than A. And I'll leave the definition to you. You probably can can figure that out. So here's an example. Roll a pair of fair dice. That was example 2. Example 2 above. Now what is the probability that x is at most 3? Well, how many ways can you make when you roll a pair of dice? How can you get a number that's less than or equal to 3? Well, the only way to do that, that's the probability of the following event. It's the event, you can get a pair of 1s when you roll a pair of dice, or you can get a 2 and a 1, or you can get a 1 and a 2. And that's the only possibility of getting a number less than 3 when you add up the dice. So this would be 3 out of 36, or in other words, 1/12. Okay, so that's that. Okay, so we're going to take the previous notations and turn them into definitions. Definition. The function. So we're given a random variable x. We define the probability mass function of x is the function from R to R. It's sometimes called P, and P of A is given by taking the probability that x equals A. Sometimes they use the notation also denoted P, the probability mass function is sometimes denoted f sub x of A, which is P of A. So that's a function from the real numbers to the real numbers. That's the first one. And then there's another function that's very important called f sub x, which also goes from R to R. And f sub x of A is given by the probability that x is less than or equal to A. And this is called the cumulative distribution function of the random variable. So these are associated to a random variable. Okay, so for example, we have the probability mass function. Oh, by the way, this is notation, so, or abbreviation. PMF, when I write that, I mean the probability mass function. It's just an acronym. And we have CDF, which is the cumulative. So this would be little p distribution function. And it's f sub x. And sometimes if fx is understood, we write just f. We just get rid of the subscript. Okay. All right. So we have the PMF and the CDF, right? So for example, for rolling a pair of dice, we have the following. We can graph this function, the PMF, the probability mass function of rolling a pair of dice. Now, when you roll a pair of dice, you have 2, you can get 3, you can get 4, get 5, you can get 6, get 7, you can get 8, 9, 10, 11, 12. Now, there's only one way to make a 2, and the probability of making a 2 is 1 out of 36. So here you got 1 over 36, 2 out of 36, 3 out of 36, 4 out of 36, 5 out of 36, 6 out of 36. Okay, so there's only one way to make a 2, so it's 1/36 probability of building a 2 from rolling a pair of dice. There are 2 ways to make 3, so that gives me a probability of 2 out of 36, or 1/18. There are 3 ways to make 4. There are 4 ways to make 5. There are 6 ways to make 5 ways to make 6, I guess. And there are 6 ways to make 7, right? How do you make 7? 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. And you want to make 8, there are only 5 ways to make 8. And there are 4 ways to make 9, 3 ways to make 10, 2 ways to make 11, and 1 way to make 12. So this is what the PMF of a dice, rolling a pair of fair dice looks like. So that's a graph of it. So here's an example. So let's flip a coin until heads occurs. And let's assume it's a biased coin. So a biased coin. So that means the probability of heads is P, some number, it's not necessarily a half, and then it's not 0. So what is the sample space? Well, you can get heads on the first try, or you can flip it twice, first getting a tails, then a heads, or you can flip tails, then a tails, then a heads, or you can flip a tails, 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 then a heads, and so on. Okay, so now what's the probability of say, tails, tails, all the way, the number of tails, say maybe k minus 2 tails, and then a single heads. Let me say k minus 1 tails and a single heads. So a probability of tails is 1 minus p. There are k minus 1 of these tails occurring, so it's 1 minus p to the k minus 1. Then we have a probability of p occurring. And so that's the probability of that event. So now from that we can compute the PMF. So P of 1 is the probability of, oh yeah, so what is the random variable? Let me make up a random variable now. Let X be the random variable which records the number of flips that I have to make. So then what is the probability mass function? Well, it's the probability of P of 1, that's the probability of X equals 1. And that would be P because you would get a heads on the first try. If you flip it only once and you stop, you're done. What about the probability of 2? Well, by the calculation that I made back up here, it would be 1 minus P times P. What's the probability of 3? It would be 1 minus P quantity squared times P. In general, the probability of n flips occurring is 1 minus P to the n minus 1 times P, just like we computed before. And so here's the question. Why is this actually a probability mass function? Well, notice the probability mass function, I should have said this, but a probability mass function is a property of it, of a PMF. The sum of P of K is going to be the sum of P of K, where P of X, let's say X is over all real numbers, X any real number, has to add up to 1. Okay, so let's see why that's true in this case. Okay, so here the X's are the places. This is called a discrete random variable because the values on the real numbers, which give you a value of P, can only occur at integer points. It doesn't make sense to talk about P of 1/2, for example. So let's compute this. Okay, so I need some space, so let me save this and do the computation. Okay, so let me erase. So I want to show you why the sum adds up to 1 in this case. Well, what's the sum of P of K? K goes from, we always have at least one flipped. K goes from 1 to infinity. By the way, in this case, the sample space is an infinite space because you might have to flip forever. You might never get heads. So what is the sum? Well, it's the sum, K goes from 1 to infinity, of 1 minus P to the K minus 1. Oops, I made a mistake here. The n minus 1 goes outside. So it's 1 minus P to the K minus 1 times P. I can factor out a P to get the sum K goes from 1 to infinity of 1 minus P to the K minus 1. Now, there's a formula that you learned. We talked about this formula once. The summation x to the k, k goes from 1 to infinity. Well, k is going to go from 1 here to infinity, but it's a k minus 1 in the exponent. That's the same as the summation x to the k goes from 0 to infinity, is 1 over 1 minus x. It's a geometric series, which you learned in Calc 2. So this sum you get is going to be equal to P times 1 over 1 minus 1 minus P. By the way, this is only true if x is less than or equal to 1, but we know that since P is not 0, this number, the x in this case, is 1 minus P, and so that's never 1. So this is only true, this statement is true if x is between 0 and 1, let's say. Actually, x could be between minus 1 and 1. In any case, this is what you get. And what is this? Is P times 1 over P, which is 1, and that's what we needed to get. So we just verified this actually, this expression here, the sum of all the values of the PMF adds up to 1. Okay, so I want to do example 2A in the text. Actually, so this is 4.2, example 2A on page 125. So I want to, it's describing a PMF for a random variable x is given by P of I is given by some constant times lambda to the I over I factorial. And I is going from 0, 1, 2, and it goes, so I varies over all the natural numbers. So I'm going to ask some questions. Here lambda is some non-negative number, and C is some constant, which we don't know yet. So so what's C? So part A of the question is, what is C? That's the first part, and I'll talk about the remaining parts in a moment. So to compute what C is, we look at recall that summation K goes from 0 to infinity of P of K has to add up to 1. That's telling me that the sum K goes from 0 to infinity, we stick in the value of P of K, that's C, lambda to the K over K factorial must be equal to 1. I factor out a C, we get C times the sum K goes from 0 to infinity, lambda to the K over K factorial is equal to 1. Now this summation is if you recall your exponential function, this tells me that, remember, that e to the lambda is equal to this sum. That's also from Calc 2. So therefore, c times e to the lambda equals 1, and that tells me c equals e to the minus lambda. So that's part A. Okay. So we know that P of k is equal to e to the minus lambda, lambda to the k over k factorial. So now we have the complete expression for the PMF. Okay, so now let's compute some expressions that the book asks us to compute. This is B. It wants us to compute P of 0. Well, that's easy enough. We just set k equal to 0 in P of k. So we get lambda to the 0 over 0 factorial. 0 factorial is 1, by the way. So lambda to the 0 is 1, so we get e to the minus lambda. So that's simple. Okay, so what about part C? Part C asks us to calculate the probability that x is strictly larger than 2. Now, this is easy because this is the same as 1. So what's the complementary event to x being less than greater than 2, strictly greater than 2? That's 1 minus the probability that x is less than or equal to 2. So this is the complementary event, x. Okay, so then what is that? That is, remember, x can only, the values of x, for x less than or equal to 2, that means that that's 1 minus the probability that x equals 0, or the probability that x equals 1, or the probability that x equals 2. In other words, 1 minus p of 0 plus p of 1 plus p of 2. Okay, so how do we get that? So that's 1 minus, we know p of 0 is e to the minus lambda. We know what p of 1 is because we computed p of k. P of k is at the top of the slide, and that's e to the minus lambda times lambda to the first power over 1 factorial. And then p of 2 is given by e to the minus lambda, lambda squared over 2 factorial, but 2 factorial is 2. So you can rewrite this as 1 minus e to the minus lambda times 1 plus lambda squared over 2. And that's the answer. Okay. So, what is the PDF? What is the CDF of this random variable x look like for this PMF? Well, here's the deal, right? P of k is defined when k is 0, 1, 2, etc. Right? So, let me write down the first few values. P of 0 is e to the minus. Let's take a special case, lambda equals 1. Okay, just for fun. So it'll be e to the minus 1, and then p of 1 would be e to the minus 1 again, because lambda is 1. I'm taking lambda to be 1. P of 2 would be, stick in 2, we get e to the minus 1 times a half. And p of 3 is e to the minus 1 times 1 over 3 factorial, which is 1/6, and so on, dot, dot, dot. Okay, so now if we want to start computing f sub x of 0, Well, that's going to be the same thing that as the probability that x is less or equal to 0. But 0 is the only value that occurs in that interval, so that's p of 0, which is e to the minus 1. Then we have f of sub x of 1. That's the same as p of 0 plus p of 1 in this case. And that's e to the minus 1 plus e to the minus 1, but we calculated on the left of the slide. So now if you're a number between 0 and 1, so if t is less than 1 but greater than or equal to 0, then there are no values of p between 0 and the PMF between 0 and 1. So you're going to get f sub x of t in this case is given by p of 0 still, which is e to the minus 1. And similar things occur. For example, we have f sub x of 2 is p of 0 plus p of 1 plus p of 2, which we could add up the first three. We get e to the minus 1 plus e to the minus 1 plus e to the minus 1 times a half. And if you number less than 2 but greater than or equal to 1, you get back f sub x of 1. So what I'm trying to say here is that the graph of the CDF, the cumulative distribution function in this case, looks like the following. You get e to the minus 1, and then between 0 and 1, but not including 1, it's constant. At 1, it jumps to e to the minus 1 plus e to the minus 1. So this would be e to the minus 1 until you get to 2. And then at 2, it jumps again, gets bigger, and so on. So then you get to 3, it jumps again. And the point is that this is called the step function in this case. So that's what the CDF looks like in this case. And typically, a CDF will look like a step function for a discrete random variable. Well, that's it for the week. I'm going to stop here. Have a good weekend.